All right, in this section 1.6, we're going to do a brief introduction into molecular orbital theory. So the essential concepts are listed here. So basically, covalent bonds, they originate from atomic orbitals, right? So individual atoms, their orbitals can overlap, and when they do that, they will form molecular orbitals, right? So these molecular orbitals will be three-dimensional regions where the electrons can exist, forming bonds. And minimum energy, wherever there are minimum energy wells, that will correspond to maximum stability. Two atomic orbitals, when they combined, they can give rise to a bonding molecular orbital and an anti-bonding molecular orbital. And we will see a graphical representation of that. Cylindrically symmetrical bonds are called sigma bonds, and side-to-side overlap of parallel p orbitals, when they're in phase, form bonding pi bonds, right? And the bond strength is measured by how much energy it takes to dissociate that bond, and that energy is called the bond dissociation energy, right? So the Lewis model, it fails to take into account the wave-like properties of electron, right? So this molecular orbital theory, it accounts for both particle and wave-like behavior. Molecular orbitals describe volumes of space around molecules where electrons may be found, right? So that's what I was just saying. So we can move on to our next slide. So here we go. If we have two atomic orbitals, a 1s atomic orbital for hydrogen here, and here's an electron, and then another 1s atomic orbital here, and they come together, we can have overlap here, and then we can have a molecular orbital. As the orbitals begin to overlap, there is a decrease in the potential energy because each electron is attracted to both of the nuclei of the atoms at an optimal degree, but the electrons, their repulsive forces, they are optimized, they're decreased at an optimal degree. So we can look here on the x-axis, we have internuclear distance, right? So as we go this way, the distance is increasing. And as we go this way, it's decreasing. This is graphically represented here. The atoms are getting closer together, and on the y-axis, we have energy is increasing, right? So the energy of the system is increasing. And as I said on the previous slide, as energy decreases, we're more stable. So we want to go down here. We want to go down on this axis because that would be corresponding with a more stable system. So as the internuclear distance goes this way, we can see this red line moves up in energy. So as these two hydrogen atoms get closer and closer together, their nuclei are getting closer together, and it looks like this energy is increasing. However, as they get further apart here, there is this optimal distance. This is an energy well here. And at 0.74 angstroms, this is the minimum, right? So this is the minimum energy in that energy well, where this is the optimal force, where the attractive forces and the repulsive forces are relatively equal, right? And you're at the bottom of the energy well, and it's very, very stable. Here, the internuclear distance is increasing, right? So the attractive forces are starting to increase and the repulsive forces are decreasing. Here, you are starting to get so far apart that the attractive forces are no longer mattering, really. And here, the atoms are so far apart that there is no real attraction between them at all, and no bond will be forming. So here at the bottom of the energy well, we have the most stability. The bond has formed. Here, this is the most stable. So this is a wonderful chart to try to understand what's happening. And the bond dissociation energy for the homonuclear diatomic hydrogen is 105 kilocals per mole. So this is a very fun way to visualize this concept, the formation of a sigma bond. So we can move on to our next slide. So, the formation of bonds, as you might have just seen, you go down in the energy well. So there's a release, a relative release in energy. Breaking bonds requires energy. You have to put in energy to overcome that optimization. So it requires energy. And it's the same magnitude, right, for the same bond. And you might remember from general chemistry, bond enthalpy, right? You just change the sign of delta H for whatever reaction that is occurring, right? So H2 bond is 105 kcals per mole. The formation of that bond will be one sign, and the breaking of the bond will be the other. So now we should briefly recall constructive and destructive interference, right? If I have one wave here and we are going up in amplitude at the beginning, and this wave is the exact same wave as is numerically represented here as 1A and 1A here, it's going up in amplitude at the beginning. We sum these waves together, we get 2A here. See, it's double the amplitude. This would be constructive interference. And if we look at destructive interference, this bottom one is now in the negative region at the beginning, and the top one is in the positive region in the beginning. You add these together, and then we have a resultant wave that has zero amplitude throughout. This is important to recall because, again, electrons exhibit particle and wave-like behavior. So when we start to mix our atomic orbitals, it would make sense that we could get bonding and anti-bonding orbitals. So the constructive combination of two s atomic orbitals is going to be a bonding sigma molecular orbital, whereas the destructive combination of two s atomic orbitals would be what we call a sigma star anti-bonding molecular orbital. And of course, it is always great to be able to graphically represent things. So again, we have our little graph here where going up on the y-axis is up in energy. So here we have an atomic orbital, or AO, or 1s atomic orbital. Over here we have another 1s atomic orbital. And if they destructively combine, then we will have a node. Here is our node here, and they're going to destructively combine to increase in energy. Remember, that is a destabilization interaction to form a sigma star anti-bonding molecular orbital. Remember, this is a molecular orbital, and there's no electrons here. But if they constructively combine, that is a stabilizing interaction. And now we have two electrons here. Here's the one electron, two electrons. Remember, there's one electron here, there's one electron here. They can come together and form constructively, right, this molecular orbital, right? This is a lower energy, more stable. It's bonding. And when you discuss bond order is equivalent to your bonding minus your anti-bonding. And your covalent bond strength increases as your degree of overlap increases. So those are some concepts, just some general concepts to keep in mind. So what happens when you form a pi bond, right? So if you have two p orbitals and they overlap, you have to have side-to-side overlap, right? If you don't have, parallel overlap, if you have one that looks like this and one that looks like this, well, they're not parallel at all. They're offset. So you're not going to have side-to-side overlap. They have to be at the same angle. So when they overlap perfectly, then you're going to get two in-phase orbitals overlapping to form a pi bonding molecular orbital. And you're going to get one nodal plane, and this results in lower energy, very similarly to the last graph I just showed you for the molecular orbital of two s orbitals overlapping. You'll get the decrease in energy to form the pi bond, right? And a pi bond is going to be a double bond, right? And then you can also have destructive overlap. See how these orbitals are not in phase? You have the white here on top and the orange here on top. And then now you'll get two nodal planes. So another way of thinking an increase in energy would also be an increase in nodal planes or an increase in nodes. So of course we get a pi star anti-bonding molecular orbital here. So it's pretty much an analog to the formation of a sigma bond. And so to conclude, we will move on to 1.7 for our next video.